Hello friends, in this video we discuss Kuttaka, Bhavana and Chakravala method, a computational aspect. This is part 1 of the video and in part 1 we shall discuss Kuttaka method. Indian mathematicians in the ancient period came up with several original ideas and made tremendous contributions in the mathematics that we know. In particular, they found ingenious methods of solving linear and quadratic indeterminate equations, that is Diophantine equations. These methods are well known by the names Kuttaka. We use Kuttaka method to solve linear equation of the form ay minus bx equal to plus or minus c, where a, b, c are positive integers. Then Bhavana and Chakravala methods are used to solve quadratic equation of the form nx square plus k equal to y square, where n and k are integers. First, let us discuss the legacy of Kuttaka method. Kuttaka means pulverizer, that means to break into smaller pieces. The first explicit general solution to ay minus bx equal to c was given by Aryabhatta in Aryabhatiya. Then Bhaskara I gave 30 examples in his commentary on Aryabhatiya. Brahmagupta made an elaborate description in a separate chapter, Kuttaka Adhyaya, in his famous book Brahmasputa Siddhanta. A lucid algorithm presentation we can found in Bijaganita of Bhaskara II, a chapter Kuttakara in Yukti Bhasha of Jeshtadeva. So, a systematic investigation of Diophantine equation began in Europe in 16th century. After 1000 years it was done in India. So this is a very proud moment for us. Now let us discuss the method. Problem: find all positive integral solutions of ay minus bx equal to plus or minus c, where a, b, c are positive integers. The GCD of a and b must divide c, and hence we may divide the equation by GCD of a and b and reduce the coefficients. It is sufficient to solve the equation ay minus bx equal to plus or minus 1. Then we can multiply both sides by a suitable constant c. It is enough to find a minimum positive solution for generating all other solutions. In fact, if alpha beta is a minimal solution, then all solutions are of the form alpha plus ta, beta plus tb, where t is a positive integer. One may assume that a is bigger than b. If a is less than b, then we can interchange the roles of a and b. Now let us discuss the method. It is enough to find minimal positive solution of ay minus bx equal to 1, where a and b are positive integers. We know that the repeated use of division algorithm, that is Euclidean algorithm or long division, we can produce the following steps. We have assumed that a is bigger than b, so you divide a by b and then we get remainder r1. Then divide b by the remainder r1, then you will get remainder r2 and so on. So in finitely many steps, we get the remainder rn and we stop there where rn is 1. Then we define the quantities xm by backward substitution as follows. Xm equal to am xm plus 1 plus xm plus 2, where xn plus 1 and xn plus 2 are particularly chosen by using the following equation. Rn minus 1 xn plus 2 minus xn plus 1 equal to minus 1 raised to n. N is the number of steps where we stopped. Now consider this equation again. Rn minus 1 xn plus 2 minus xn plus 1 equal to minus 1 raised to n. If n is odd, then we may choose xn plus 2 as 0 and xn plus 1 as 1. If n is even, we may choose xn plus 2 as 1 and xn plus 1 as rn minus 1 minus 1. Then x1 x2 is the solution of the equation ay minus bx equal to 1. Now let us solve concrete examples. So consider 60y minus 13x equal to 1. Here a means coefficient of y is bigger than b, which is coefficient of x. So you divide 60 by 13 and then we get the following steps. And in the fifth step, observe that R5 equal to 1. So in the fifth step, n equal to 5, we get a remainder 1. So these are A1, A2, A3, A4, A5 and R4 is 2. Now we need all these values in the next step. Consider the equation minus 1 raised to n equal to Rn minus 1 xn plus 2 minus xn plus 1. Then n equal to 5, which is odd, so we can choose x6 equal to 1 and x7 equal to 0, and then by backward substitution we can find x5, x4, x3, x2 and x1, and now we know that x1, x2 is the solution. So solution of the given equation is x equal to 23 and y equal to 5. Consider another example, 53y minus 12x equal to minus 4. Then 53 is bigger than 12, so you divide 53 by 12 and then we get the following steps. First we consider 15y minus 12x equal to 1. So we get these values. Then again, like last example, consider this equation and then as n equal to 3, choose x4 equal to 1 and x5 equal to 0, and then by backward substitution we get x3, x2, x1. So x1 equal to 22 and x2 equal to 5 is the solution. But this is solution of the equation 53 into 5 minus 12 into 22 equal to 1. But in the original equation, constant was not 1, constant was minus 4. So multiply both the sides by minus 4 and then we get these coefficients. But we want a positive integer solution. So minus 20, minus 88 are negative integers. We don't want negative integers. So minus 20 we can write as multiple of 12 plus some positive integer, and same multiple we have to use for the another term. So we get this expression, and then cancelling the common terms we get 53 into 4 minus 12 into 18, which is a positive integral solution. Now consider the case 21x minus 8y equal to 155. Here a is less than b. So first you consider the equation where constant is 1. Then divide 21 by 8 and we get these steps. Then these are the important values that we need for further calculation. Consider this equation again. Now here n equal to 4 means even. So you choose x5 equal to 1 and x6 equal to 1. Then using backward substitution, we find these steps x4, x3, x2 and x1. Now here the case where a is less than b. So now x2, x1 is the solution. So solution of the equation is 21 into 5 minus 8 into 13 equal to 1. But we want the constant as 155. So multiply both sides by 155. Now here we get positive integers 775 and 2015. But these are very large. We want minimal positive integral solution. So you write 775 as multiple of 8, suitable multiple of 8, and the same multiple we have to use to express 2015 as a multiple of 21. Then cancelling the common terms we get 21 into 15 minus 8 into 20. So method is same whether a is less than b or a is bigger than b. Then consider 71x minus 15y minus equal to minus 5. Here also we have a is less than b. So first let us solve 71x minus 15y equal to 1. Divide 71 by 15 and then we get these 4 steps and we find all these values which are useful for further calculations. Then consider this equation again. Now n equal to 4, which is even, so we can choose x5 equal to 2 and x6 equal to 1. Then using backward substitution, we can find x4, x3, x2 and x1. Now x2, x1 is the solution. So 71 into 11 minus 15 into 52 equal to 1. But we want constant as minus 5. So multiply both sides by minus 5. And then the solution is minus 55 minus 260. But we don't want negative integer solutions. So we have to express minus 55 as a suitable multiple of 15 plus some positive integer. Then cancelling the common terms, we get 71 into 5 minus 15 into 24. So this is the final answer. Let us discuss one example where we can reduce the coefficients of original equation. Consider 100y minus 63x equal to minus 90. Now there is no common factor between 100 and 63, but there is a common factor between 100 and 90, and the GCD of 100 and 90 is 10. So we can reduce the coefficients of original equation so that it is easy to solve the equation. Let A1 be A upon G1, which is 10. Then G2 is the GCD of B, means 63, with C upon G1, means 9. Then GCD of 63 and 9 is 9. Then divide B by G2, so we get B1 equal to 7. Now the original problem reduces to 10y minus 7x equal to minus 1, and these numbers are very small as compared to the original equation. Now we can easily solve the reduced equation just by observation also. We can check that x equal to 3 and y equal to 2 is the solution of the reduced equation. Now we can find the solution of the original equation by this solution. Now the solution of the original equation is x equal to 30 and y equal to 18. In this way, if coefficients of the original equation are very large, and if the GCD of A and C is not 1 or GCD of B and C is not 1, then we can reduce the equation to smaller coefficients, and that will help us in calculations. Now these are exercises. You can try these exercises by Kuttaka method. Practice is very important, and you can solve these exercises. These are some references. I took material of these slides from these references. So you can read these references. Thank you.